Good afternoon, everyone. Today, I will give a brief presentation of the detection of urea present in water using a disposable paper-based sensor with the fractional order Colpitts Oscillator. So this is the outline of today's presentation. I will go through the introduction, objective, urea sensor, then EIS and EM model, then what is fractional order element, and then the proposed signal conditioning circuit, and the experimental results and the conclusion. So in the introduction, we will know there is how the urea is being present in the water, what is the source of urea contamination in the water. But main focus area we will put here, the limit of urea concentration should be in the domestic storage will be 30 milligram per DL. For the industrial storage, that should be 300 mg per DL, and for the fishery industry, it should be 100 mg per DL. So there will be the question how to measure it. So we need a meter. So in the literature, there are the spectrophotometry, colorimetry, fluidometry techniques are there, which need costly instrument and also the trained engineer or labor, and it is not portable in nature. So if we ask a farmer to buy a instrument of 50,000 or 10,000, it will not feasible. So we have to make a portable and also economical instrument. So from there, we propose that the impediometric based sensing measuring urea concentration directly measured from the impedance, and the electrical equivalent circuit when we propose, and that is the series combination of some resistor, capacitor, and fractional order element. And we should note that it is reported the sensor stability, sensitivity, and range could be further improved if a suitable signal conditioning circuit will be there. So from there, we have the objective. We should have a low-cost sensor fabrication, study the equivalent electrical modeling, design a suitable sensor interfacing circuit, and we will propose a portable meter. So now this is the typical sensor what we have proposed. This is the paper-based sensor where we use the wax urea coating for the enzyme-based electrochemical sensor. This is the typical figure of the paper-based disposable sensor. We can use it for at once, and it will cost around 1 rupee. And if we go for the mass production, it will lesser than that. So we will use these deep into the sample, and these will go to the LCR meter. So this is the average impedance. We have taken the relative impedance for that, and it is showing a linear response from 1 mg per DL to 1000 mg per DL with standard deviation less than 5%. So this is the typical EIS plot. We will take the Nyquist of these samples for different urea concentration, and we will see there is a change in Nyquist plot that can be detected. But from a graphical interpretation, this is a quite challenging task to take out the parameters from the graph. So we will propose the electrical equivalent model, as in we are electrical engineers or sensor engineers. We will go on for the electrical parameters, and this is the part we found the sensor and the interface and the whole whole electrochemical system has the modeling of this. I will go on through the what is CPE. I hope most of the people are not knowing about the CPE. I will go to the detail of CPE. So we will use this electrical equivalent model using the ZView software, and this is the fitted curve and the experimentally getting curve, and we will have a good fitting result. And so for that, we will have the concentration with these parameters R1, F1, alpha 1, F2, and alpha 2. We will show here there is a strong correlation with these 5 parameters are present. But please you may please pay attention here. These parameters are not readily available. If you take a meter and take the impedance on a selected frequency, on a particular frequency, we will not get this parameter value. So getting this parameter value, you have to take the impedance, what we done for 20 Hz to 2 megahertz. Then you go for the ZView software, and then you will have this parameter value. So you will tell you are proposing a portable meter. So how would we doing this thing? So this is the challenge we have faced, and we have proposing a quite small, little, and low cost portable meter circuit. So this is the fractional order element, what we are having. There's the fractional order element, also known as constant phase element, is a generalized representation of a resistor, inductor, and capacitor. The impedance of the Laplace transform of fractional order element is ZF is equal to 1 upon F s to the power alpha, and the frequency response showing that it is showing a constant phase nature. So that's why its name is constant phase. So but in practically, it is not showing the constant phase, but it is showing constant phase for a limited frequency zone and also have a little bit of phase band. So all of the model parameters have a strong correlation with the urea concentration. But what I am saying that taking the impedance data, you need the costly LCN meter. After that, you have to put these data to the ZView software to having these electrical parameters that and also the costly software and the computer. So this is not suitable for the portable meter. So we proposes a fractional order Colpitts oscillator, which will incorporate the sensor itself into its circuit. And if the parameter changes, the oscillation frequency will be changing. So by detecting the oscillation frequency, you can detect the concentration of urea. So this is our proposed fractional order Colpitts oscillator, which incorporate RCP parallel. So now there is in this electrical equivalent model, you see there is two models are there, one RCP block and one CP. But for understanding, we know these blocks are not dominating in the whole frequency range. So for a particular frequency range, this first block will be dominating, and for the other, the second block will be dominating. So we found out this first block is dominating for the higher frequency range, and for the second block, it is dominating lower than the 200 Hertz. So we have two mode of operation. So when we do the mathematical derivations, we found that for the mode 2 operation, the resistance ratio, this RC1 divided by RC2, which is called as the critical resistance to having the sustains oscillator for oscillation for the Colpitts oscillator, it founds to be negative. So the mode 2 operation will be not possible. So we will go for the mode 1 operation. So this is a typical our experimental setup. We have managed to have a clamp setup. This is our typical sensor. We dip into the sample, and this is our small fractional order Colpitts oscillator for the sensor interfacing circuit. So here we found that for the different concentration, it is showing the change in the oscillation frequency. And for this, we have noted that the LOD of our system, it can detect from 3 mg per DL to 330, and here 330 mg per DL. And if we go for a curve fitting equation, it is showing a linear curve fitting. So from this equation, you can find the concentration of the urea by detecting the oscillation frequency. So in the conclusion, we can say we have developed a novel paper-based urea sensor for detection of urea present in water sample. It uses fractional order Colpitts oscillator, which incorporate all the spectrum of these impedance from 20 Hz to 2 MHz through only using a simple circuit. So, and the LOD is 3 mg to 330 mg, and the sensor response is linear, having sensitivity of 160 kilohertz per decadal chain. So these are all the references, and thank you. We thanks EPISCON 224 to giving us opportunity to present our research work. Thank you.